Dear students, we're going to discuss today about the data analysis part. And while we were taking measurements, we come up with a certain errors, some mistakes. There are reasons, there are chances for mistakes. How can we deal that kind of mistakes? And I'm sure you already watched the other two videos so that you already know how to use our instruments like vernier caliper and micrometer. And so before we going to the data analysis part, let me quickly discuss you about the possible errors. Yeah, the first kind of errors here we mentioned, uh, they are personal errors. The errors due to our inability to read some instruments. Sometimes, most of the times, this can lead into big mistakes. Imagine, if you are not properly trained how to use the vernier caliper or the micrometer, you will end up with the mistakes. So these kind of errors we called personal errors. I mean, how we can avoid this kind of error? We need to be familiar with the measuring instrument. That means you need to be very well trained. That's the way we can avoid such things, and even errors due to the miscalculation and etc. we will call personal error or mistakes. And the other kind of errors, even though if you are very familiar with these instruments, there sometimes we will end up with errors because of the flaw in the instrument, because of the mistakes, because of the errors, because of the mistake of the instrument. Sometimes the faulty instruments will lead you to mistakes. So these are the error we call systematic error associated with the measuring instruments. And there are some other reasons, random reasons are there to lead into mistakes. So that's we called a random error. That means it is due to the unpredictable and unknown variations in the total experimental process. That means, the sometimes, the experimental process is wrong. If you have a wrong experimental process, we will be ending up with the mistakes. So these kind of errors we call random error. Example, if I can say a simple example, imagine you are measuring you're using a balance to measure its mass. And while you are measuring mass, imagine you are in a closed room and somebody closed the room and somebody opened the door and closed. This will induce some pressure in the room, right? And so the mass that you measure will showing a different value. So there are so many ways we may end up with errors or mistakes. So while you performs experiments, you need to be aware about that and you need to avoid such errors. That's the importance of these things. Now, let us move to the significant figures. Yes, this is a very important point. That means while you are measuring, while you are taking measurements, you will end up with these kind of numbers, right? Let's say, imagine you are measuring a length of a cylinder, and you know, in reality, imagine if this cylinder you cut for 40 millimeter. Okay, so imagine you are measuring a 40 millimeter cylinder. If you look into this 40 millimeter, how many significant figure here? It's only one significant figure in maths, right? Now, let's say imagine you measure the height and you end up with this height while you are using your vernier caliper. You have taken a reading and it is 39.82. This is the reading 39.82 millimeter. Let me ask you how many significant figure here. Yes, your measurement has 4 significant figure, and whenever you measure this a cylinder with that particular instrument, you will always have 4 significant figures. So that means imagine you have a reading and which is 40 while you are using the same instrument. That 40 means 40.00. You must write this way. That means you are maintaining the same significant figure. That instrument can provide how many significant figure here? 4. So that's the reason, we just giving you a very little idea about significant figures, and already from the maths class you learned the maths and chemistry, and from the schools you already know how to count the significant figures, right? Anyway, here how many significant? 4 here, 4 here. How many significant figures? This has 4 significant figures because, okay, these rules, right? I'm not going to spend time on that. Okay, next thing. Yeah, these are the rules also you will be always consider while you are doing any kind of calculations, right? That means we always maintain while you are, imagine you are adding or multiplying, we are adding or multiplying some measurements that we have come up with. But always while you are reporting your final answer will be in terms of the least significant figure in your measurement. The one you used here, if you look into this, every numbers are in 4 significant figure, and when we add, you get this. So that means the answer of that final measurement or the calculation, you need to maintain the same significant figure. How many are there? The everywhere 4, so you need to maintain 4. Here you look here in the multiplication case, imagine you are finding the area. That means if this is length and this is width, so the area will be this. But look here in this measurement, this has 5 significant figure, this has 3 significant figure. So your answer will be in terms of the least significant measurement. What is the least significant measurement significant figure here? 3. So that's why you maintain 3. And this is a rounding rule. You know that if it is 16.22, it will be, yeah, it will be always round into one the decimal place. And next thing, and of course you know that this is 16.25, so we will count into 16.3. Now yeah, this is if you look into this, these, imagine if it is the length of a cylinder that you measured. In fact, you will always get a very close reading, but this is just a data. Look here we have 4 readings. So imagine you measure the length of that particular cylinder and you come up with the 4 different readings. So which one will be the accurate answer? We cannot say that none of them are accurate. So we will use always the statistical method. That means we'll find the mean. You know how to find the mean. That means you will add everything and divide by 4. So you will get the mean, and here the mean value is 19. But actually, imagine you come up with an answer which is 19. Imagine you come up with an answer which is 19. You think the 19 is correct? 19.00. Anyway, they maintain the 4 significant figure. Anyway, my question is, the 19 is the correct answer? No, because you know none of your measurement is 19 anyway, but you actually your mean value is 19. But when we do measurements and when we are going to talk about your measurements, this time we need to talk about the uncertainty in your measurement. What you can calculate the error in your measurement, and you always talk to I mean, whenever you take any measurement, your final answer will be report in terms of certain limits. So you will say that my value is lying in between these. And look at this case. Here we are using a simple statistical method, and that is what we called, we are taking the mean deviation, or we are taking the average deviation. Actually, what is this? Look into here, we have an absolute value. You can see here it is what? An absolute value of the mean value minus individual measured value. That means absolute value of x bar minus x. X bar represents the mean value and x represents the individual measured value. Here 18.60 is the individual measured value and the mean value is 19. So the absolute value of 19 minus 18.60, it represents 0.40. And what is this? The second measured value is 19.30. So what is the absolute difference between the individual measured 1930 and the mean value? It is 19 minus 19.30. So it will be 0.30. Because of absolute value, you will be always keeping the plus sign. So that's the way all the 4 measurements we have. So what is the mean of this deviation? We just add everything and divide it by 4. So this is the mean value of the deviation. That means your final answer is 19 plus or minus 0.85. So you will be reporting that length measure in these terms. So what does it mean? It represents that you are sure that the measured length is in between 19 minus 0.85 to 19 plus 0.85. 19 minus 0.85 will be 18.15, and 19 plus 0.5 means 90, plus 0.85 means, so that means you are declaring while you are taking any measurement, you are not sure about the reading, but you have certain percentage. You can say in statistics there are so many rules are there to say the uncertainty. But anyway, here we can say you are almost sure, you are maybe 90% sure that your measurement is lying in between 18.15 and 18.15 and 19.85. So this is the way we are going to take all our measurements and representing these data into our records. So what does it mean? The length you measured is 19 plus or minus 0.85. That means this is the length you measured, and this part is we call the uncertainty you measured. So we call it delta error or error you measured. Actually, we use the statistical method. Which statistical method? We use the average deviation method. There are so many statistical methods, but in this case we use, in our all experiments, we are going to use this method, the mean deviation or average deviation, as the uncertainty. You know that there are so many other methods, standard deviation and etc. But anyway, we are going to use these rules. Anyway, now if you move into the rules, I will talk about the propagation of error propagation. Okay, we are continuing with the error propagation. That means when we do measurements, there will be an error with every measurement. But we are going to discuss about the propagation of error. What does it mean? Imagine you wanted to calculate the area of a rectangle. Let's say that means we know that area is length into width. Of course, when we measure length, there is an error associated with the length. We call delta L. And when we measure the width, there is an error associated with that delta W. So what will be that means error in length and error in width measurement will lead an error in the area measurement, and that is delta A. Then how will you calculate delta A? Is it delta L into delta W? In fact, no. There are certain rules. You don't need to worry about how these equations comes, because I'm not going to explain you that, but I will just give you an idea. We understand here the error in area is a function, or it depends on the error in the length measurement. That means it depends on L and it depends on the width. That means let us look into the equation that we use to calculate our density. That means you remember I explained already the density of our cylinder is 4m pi d square h. That means when we measure the mass, you understand that there will be an error. We know how to calculate it. It is we call delta m, and there is an error associated with the diameter. We call delta d, and there is an error associated with the height measurement delta h. That means the density, the error in density or delta rho it depends on delta m, it depends on delta d, it depends on delta h. Actually, we can differentiate these, or there is a mathematical analysis. It is explained in statistics, and we are not bothering about that, and it is not our scope today. So what we are going, we know that it's a function. There is a function. These are the functions of these. So we will use a differential mathematical analysis, and we come up with some solutions. And I'm just going to give you only the solution. What are the equations you can use in order to solve this? You don't need to worry. You don't need to bother about the methods. You just simply understand the techniques that I'm going to explain you. Okay. Look at this. I will write here. Imagine. I told you that here, okay, let me write a general equation. Imagine if Z is a function of X and Y. That means, let's say if Z is the area. Yeah, we know that area is length into width. That means, or imagine there is another equation like our case, density equal to 4m pi d square h. Here I have m d h. So I can write a general equation if z or z, okay, z equal to a into b into c, or z equal to a into b divided by, say, this format, or it is bc divided. Anyway, here how many terms are in here, how many measurements are included? 3 measurements. So if it is 4, same rule, but I'm just going to show you a general equation which is an outcome of differential analysis. So I will write the uncertainty in the measurement of Z is delta Z divided by Z equal to delta A divided by A plus delta B divided by B plus delta C divided by C. Very simple. So imagine if you wanted to use this rule to find the uncertainty in the area measurement, A is equal to length into width. Very simple. Delta A by A equal to delta L by L plus delta W by W. From this, we know what is A. So you already know. Then how can you find delta A? Very simple. Delta A is A into this delta L. Already delta L you know, delta L you know. Already width you know, delta W you know. Now the unknown delta A can be calculated. So this is the equation we will be using if we have any if we have to find an outcome or a uncertainty or the propagated error in while we were using these kind of divisions or multiplication. That means if it is x divided by y or x into y in any format, or these any of these format, we will have the same relation. And let me show you the other part. I mean, if we have a situation like if imagine we are asking you to calculate the perimeter, or asking if we imagine we wanted to add two cases, like the total length is the first length the measurement L1 plus the second measurement L2, or if you wanted to find a, a, a case where let me write the general equation. If A is x plus y, or if A is in the case A, if A is equal to x minus y. That means if A is in any format, x plus y or x minus y, how will you find the uncertainty in the area? Here we are not multiplying, we are adding or subtracting. Then the delta A is given by delta x plus delta y. Whether it is positive or negative, this will be the relation. And one more thing I can just help you with. If you have a case like this, that means we know that the area is L square, or we know that the volume is L cube. But here I measure the length only one time, and delta L only, we know that delta L, but how will you find the delta V? There is a general equation that means if z equal to a to the power n, that means n is the power, okay, then the rule is delta z by z is n delta a divided by a. If I use this equation, can you please help me to write this? Yes, tell me. Yeah, delta a divided by a is 2 delta l by l. Same way it will be delta v by v is 3 delta l by l. So let us do uh, our experimental objective. Here if you go all the way down, you can see that we will be using the same equations here, and here let us go through these analysis. Now here we have an option to, I'm going to show you how to fill this. Okay, look here cylinder. What is zero reading of the cylinder? That means zero reading of the vernier. That means when no, imagine when the when if you are not keeping any item in the vernier, and if you go move all the way back, the vernier is supposed to read, if no item in between these jaw, it's supposed to read 0, and if there is no error in your instrument, then it will be definitely read 0. So usually the instruments that we are going to give you is calibrated, so no 0 error. So 0 reading will be always 0. Okay. Next, this is the column. I already explained how to do this. What is this? Yeah, imagine you are going to take height. We said how many times you will take the height? 5 times. And what will be this represent? The mean height. Let's say, imagine you are going to measure a cylinder. Let's say the cylinder has approximately 2 centimeter length. 2 centimeter means 20 millimeter, right? Yeah, length. So let us say, let us take some measurements. Okay, imagine first you get 19 point, or second reading 19.99, maybe third reading 19.95, 19.93. So you have all 5 different readings. So how will you find the mean value? You know that you just add everything and divide it by 5. I'm going to guess, I'm not going to do the calculation. Let's say when you do this, it will be something 19.94 or 92, okay, 93 or something. Let's say, I'm not doing the calculation. Imagine if this is the mean value, 19.94. How will you calculate this? This means you are taking the absolute value of, you can write here mean first, and the doesn't matter because it's an absolute value. Okay, absolute value of the deviation. That means this is here. What is this? Imagine this trial. What is the absolute value of the difference, the deviation between your mean value and the individual measured value? The individual measured value is 19.9 and the mean value is 9. So 19.94 minus 19.99. So you will get, it will be 0. Minus 0.05, but you will write it will be 0. Just you don't write the negative sign. Okay, then you have all the 5 readings. You will just add and divide this by 5. You will get the mean value. What is this? This is the height, mean height. And what is this? This is the uncertainty of mean uncertainty, right? That means here your height you have right now in terms of h plus or minus delta h. So that's what here, which represents the height, it represents the uncertainty in height. The same way we will measure 5 different diameter, and you will take the mean value and you will take the mean deviation, and you will get the you will take the deviation, and here you will get the mean deviation of the diameter. Same way, you will have 5 different mass and you will get the mean uncertainty. Right now, you will be able to write all these readings. And one thing you need to make sure that here, imagine if you are going to do the mean value, let it comes this way, but you will write your answer in terms of the least measured significance here is how much? Yes, 4. So you will maintain your answer with a 4 significant figure. You get the point? Everywhere you will maintain the significant figure of your least measured value. Now, here comes the density part. Okay, how will you calculate the mean density? Of course, you know that the mean density is 4m by pi d square h. That means the m is there, mean value of the mass is there, mean value of the diameter is there, mean value of the height is there. So you will get the mean density. So you will get the mean value. Of course, your value will be in gram per millimeter cube. But how will you find the delta rho? Yes, we already learned how to use the equation. How will you use the equation? Because we know that rho is 4m pi d square h. Now let us use the equations that we learned, because here, yeah, we can say that here the 4 and pi are constant. So when we are going to do the analysis for the uncertainty, these will be ignored because the constants are not going to make any errors. So final answer will be delta rho by rho equal to, come on, 4 and pi you can ignore for the uncertainty calculation. So delta m, because the mass, delta m by m plus d square. Oh, d square, how will you do? Imagine if a is d square, delta a by a is 2 delta d by d. Oh, that means instead of d square, what you can write? 2 delta d by d plus, instead of 4h, delta h by. That means now you can find the uncertainty of uh, density, right? Delta rho is rho into bracket, yes, delta m by m plus this, right? So here everything is known. Rho you know, rho already you know because you know m and d and h. Delta m you know, m you know, delta d you know, d you know, delta h you know. So you will be able to get now the uncertainty in this measurement. That means right now you have rho and you have delta rho, but you want the final answer in terms of kilogram per meter cube. But your answer was gram per millimeter cube. So that means you need to convert this into kilogram per meter cube. Actually, the sphere part we are not doing, so we can ignore that. Okay, now, yeah, let me show you how will you convert. I mean, it is, everybody know this, but anyway, I'm going to just help you to make the conversion. So what you are going to do, you are going to convert this gram per millimeter cube into kilogram per meter cube, because you need to write the final answer in terms of that. For that, let me write this way, because you all know that 1000 gram is 1 kilogram, correct? Yeah, 1000 gram is 1 kilogram. If I divide both sides by 1000, what I will get? Yeah, I will get 1 gram is equal to 1 by 1000 kilogram. That means 1 gram is equal to 10 to the power minus 3 kilogram. Am I right? Yes. And what about 1 millimeter? We know that 1000 millimeter is 1 meter, because I need to convert into meter cube. Okay. Oh, I'm going to do the same way. I'm going to divide both sides by 1000. So 1 millimeter is 10 to the power minus 3 meter, right? So let me write here. So I'm going to write this way: 1 gram, it is 1 gram divided by 1 millimeter cube. I need to convert this, right, into kilogram per meter. So instead of 1 gram, what I can write? 10 to the power minus 3 kilogram. Is it? Instead of 1 millimeter, what I can write? 10 to the power minus 3 meter. Is it 10 to the power minus 3? So that means what I will get? 10 to the power minus 3 kilogram divided by 10 to the power minus 3 whole cube. 10 to the power minus 9 meter cube. Oh, that means I already converted into kilogram per meter cube. That means it is 10 to the power minus 3 divided by 10 to the power minus 9. Okay, that means I can write it this way, right? Because it will be going up and the sign will be, oh, that means 10 to the power minus 3 plus 9. That means 10 to the power 6. So that means in order to convert gram per millimeter cube, you just multiply that into 10 to the power 6. You will be get converted into kilogram per meter cube. So very simple. So that means imagine you are come up with an answer, let's say 0.3421 into 10 to the power minus 3 gram per millimeter cube. What you will do, if you want to convert this into kilogram per meter, you just multiply that times this value times 10 to the power 6. So this will be 10 to the power 3. Oh, 10 to the power 3 means you multiply this with 1000. That means it will be 342.1 kilogram per meter cube. Is it so easy? Yes. So this is the way you can do the conversion. Now your conclusion, you need to conclude your experiment. From this, you will be, imagine if you are end up with this answer. So you will go to the table and you will be identify this value. Of course, it will be reasonable, right? But this is not a reasonable answer anyway. So you will be getting the correct material and you will be concluding in your experiment. So now I think you almost understand everything what you're supposed to do in this report, right? Now let me show you some small things, some more things like here we understand that the multiplication and division rule, and here yeah, this is some of the things we always use in the labs. We need to calculate the percentage error. Sometimes we'll ask you to calculate the percentage error. Imagine, I mean, in most of our, I mean, let's say 2-3 experiments in our labs, our ultimate objective is to find the acceleration due to gravity, G. Everybody know that the G, I mean, we were asking you to calculate G experimentally, but everybody know that the real value, the theoretical value, or the true value of G, right? It is 9.8 meter per second square. Now, after you complete the experiment, imagine while you are doing the experiment, you get experimentally 9.7 meter per second square. So we can ask you how much percentage I mean, how good your result is. So that means we can ask you to calculate the percentage error in your experiment. So this is your experimental value and this is the true value. So how much this is deviated? I mean, the percentage difference. I mean, sorry, not the percent. We can ask you the, we can ask you to calculate the percentage error in your measurement, in your experiment. So usually we will ask this. So how can you write the percentage error? The equation is very simple. Absolute value of these difference. So you can write absolute value of these difference means 9.7 minus 9.8 or 9.8 minus 9.7, whatever. So you can write here, here they use the experimental value minus true value divided by true value times 100. That means, I mean, whether you write here experimental minus true or true minus experiment doesn't matter, but the denominator will be always true value. What is a true value? 9.8. So 9.7 minus 9.8 times 100. So that means it will be 0.1 divided by 9.8 into 100. So you'll be calculating this. This is the percentage error. And this is what percentage difference. That means, imagine we are asking you to do an experiment, and maybe we have several methods to find that. Maybe you'd use a trial, I mean, use a method A and method B, and from both the method you get the same thing. Let's say you're going to, we are asking you to calculate the room temperature using different methods. First time you measure, you get the temperature T1, and second times you measure using another method and we call it T2. So you definitely, these will be close, but there is a difference, right? And we can ask you what is the percentage difference, and for that we use this equation. Here what is this? It is absolute value of the difference, that means T2 minus T1 divided by their mean value. That means I can rewrite this, the absolute value of their difference T2 minus T1 divided by T1 plus T2, the average of T1 plus T2 divided by 2 into 100. And what is this? This is an equation. I mean, most of the times when we do graphs, you know, we will always do graphs, and sometimes you will see that the points are linear, and when we fit this into a straight line, I mean, we will get the equation y equal to mx plus c. Here m represents the slope, right? And of course, if it is a velocity time graph, the slope is velocity by time. What is the slope? Acceleration. So that, I mean, yeah, now, you know, here we already trained, we already provided the video how to do vernier caliper and micrometer, and of course you will get enough practice in the lab. And these are the equations we already discussed. Now this table I already discussed. I think I'm done with every explanations. Now this is your time to watch this video 2-3 times and to get ready before you coming to the lab. I mean, in the next meeting we'll be doing this, so that time you will be, if you watch all these, you will be very clear about what to do, and you will be easily follow our instructions. Thank you for watching and best of luck. See you soon.